On Tuesday, you've got homework 6B, which is due. And one of those problems, you're having to do a problem related to air. And you can get the fluid properties for air out of the appendix. So table A3 is where you can go to get fluid properties of air. The exam 2 that we're having on Tuesday of next week, that exam, I'm going to give you the equation sheet. It's the same one that's posted on MU Online, so it's the same equation packet that you used for the first exam. I anticipate that there will be probably 4 problems on that test, and you'll have 75 minutes to take the exam. So it'll be kind of similar in format to how we did the first test. You know, there's 3 chapters that included. Here in chapter 4, remember, we either had Euler's equation, there was Bernoulli's equation, rotational flow, convective and local acceleration. So those are some of the big concepts in chapter 4, along with flow visualization. Chapter 5 was continuity and different applications of continuity. So we were combining Q equals VA along with Bernoulli's equation and other ideas. And then we're just finishing up fluid momentum here in chapter 6. So all 3 of those topics will be included on the exam. So we're going to cover the third type of momentum problems that we've discussed. We've already done fluid jets and we've done vanes. And today we're going to look at the more specialized application of nozzles. And then also, just to kind of bring it all together, one last example having to do with the hovercraft. So any questions on these announcements before we get into the material? Yeah.
I remember on the first quiz you said that you considered that like an easy test question. For the previous quizzes that we've taken since the last exam, I consider those also easy test questions?
I don't know. You're trying to figure out how hard the test is going to be? I mean, does that really change what you're going to do between now and then? Assume it's going to be super hard. Prepare as though it's going to be a super hard test. It won't be, but yeah, I don't know. It's the one that you just got back. I thought that was pretty easy. I mean, if you apply if you knew what equilibrium was, I mean, if you didn't know what to make of that word equilibrium, then it's an impossible question. But if you did know what to make of that word equilibrium, then everything kind of just fell into place. Yes?
Will there be any short answer questions?
I don't know. I haven't written the test yet, so I can't say for certainty. I don't want to box myself into a definite yes or a definite no. So there might be. I think that it is important for you to be able to do more than just crunch the numbers. If you can explain a concept, then that shows kind of a depth of understanding that sometimes can exceed your ability to just plug numbers into an equation. So maybe. Sorry to be evasive about that. Okay, one of the homework problems that you've got coming up on Tuesday is this one. And actually, this is very similar to what we'll see when we go do the momentum experiment in the lab. We have something just like this, where there's a jet of water shooting upward, and it's impacting a cone that deflects the flow of the water. In this question, what they're asking is how high is this deflection cone going to raise? So h equals what? And the given information is that the weight of this object that's being supported by the jet of water is 30 newtons. So they also tell you the diameter of the water jet and the velocity. So let me ask you, rather than giving you the hint straight away, if you know the diameter and you know the velocity, what can you find about this jet of fluid? Think in terms of momentum, the types of things we need in the momentum equation. What can you find? Mass flow rate, right? Okay, so remember, m dot mass flow rate is the density of the fluid times the area times the velocity. And so this is water. You've got the diameter, so you've got the cross-sectional area, and the velocity is defined. And so there's going to be a certain mass flow rate of water. What do you suppose happens to the velocity of water if you've got a jet of water going up, what happens to the velocity of it? And we're saying the velocity right here at the opening is 15 meters per second. But as that water goes up through the air, does the velocity stay the same? Does it increase? Does it decrease? It decreases because gravity's slowing it down, right? So this is just this initial velocity. By the time the water gets up here to h, it's moving more slowly. So this cone is being held up by the water. The water is imparting a force to the cone, an upward force. The weight of this cone, of course, the weight is down, and the water is holding it up. So it's the impact of that jet that's supporting the cone in equilibrium. And so what we know is that the sum of the forces that are imparted by the water to the cone are equal to 30 newtons. Okay, so 30 newtons is the weight of the cone, and if it's just sitting there in equilibrium, there's a wire to hold it in stability, but we're assuming that the wire isn't in tension, it's not in compression, it's just kind of holding it in place. The force of the water impacting the cone is equal to 30 newtons. And so now look and think about the momentum equation. If we've got this cone that's deflecting the water, and here's the jet, what does CS stand for? Control circus. Control circus. No, that would be C. Surface. Control surface, right. All right. It's a control surface, right? So what we have to do is we have to decide where's that going to be. And we want to draw the control surface so that enclosed inside the control volume is all the interesting stuff that's happening. So the flow out and the flow in have to be captured. And so here's in, here's out, and if we just say we want to draw a control circus so that, I'm going to call it a control circus from now on. If we draw that so that here's the in and there's the out, then what we want to know is what's the mass flow rate in, what's the mass flow rate out, what's the velocity in and out. And we're going to be applying it in the y direction because y is vertical and 30 newtons is the weight of it that's acting downward. So we can use this momentum equation to find out the velocity of the water. Because think about mass flow rate in and mass flow rate out are equal. Like inside of this control volume, there's no possibility of accumulation. What goes in must go out. So in equals out. And does everybody understand why that is? You know, the jet of water is changing direction, but the water that comes in isn't somehow getting stored in the proximity of that cone. It's just changing the direction. So the mass flow rate in and the mass flow rate out are equal. But what is changing is the velocity. So now think about the velocity out versus the velocity in. Now the velocity in here, it's all vertical. The velocity out, even if the speed doesn't change, the direction of the velocity vector does. And so now you're going to have to take that 60-degree angle into account where only a portion of that exiting jet is in the vertical direction. And think about what would it look like if you had a cone that was intercepting the jet. This isn't two streams. This is actually a cone-shaped stream that we're just looking at a cross-sectional view of it. And so you don't have to put like 2 into the equation. It's just kind of like an outflowing jet where the velocity, only a portion of that velocity is vertical because some of it has been deflected into the horizontal. So what I'm saying is use this equation to find V out and the V in. V in and V out are going to be the same magnitude, but there's the angle that you have to take into account for the V out. So there's only The only unknown here is the velocity, and both V in and V out are the same magnitude, but it's just there's going to be an angle that you take into account for the outflow. And so then you'll know the velocity here, and you know the velocity there. And actually, Bernoulli's equation can tell you how the velocity changes as a function of elevation. Because this is a jet of water. The pressure here at the opening is 0, and the pressure up above at 2 is 0. There's some elevation difference, so the delta z is what we're going to be solving for. And you know the initial velocity and the final velocity up top, which is what you found from the momentum equation. So then you'll just be solving for the delta z. And that's ultimately what they're asking you to find, is the height that the cone will rise to. And it'll rise to a certain height that is dictated by how much force is needed to support that 30 Newton weight. So if we put on like an extra 10 newtons, you kind of already know what would happen. If we piled more weight on, it would go lower down. But then it would stop. It's not like more weight would cause it to crash all the way down. It would just go a little bit lower until it found the place where the velocity was high enough to support it. Because remember, the further down we go, the higher the velocity is. Now there's one more thing that I have to address because it may be confusing you. What is the continuity relationship? Do you remember the continuity equation? It's the main equation from chapter 5. We call it the continuity equation. What is it? Q equals VA. Good. So the flow rate out of this orifice is the same as the flow rate that's about to hit the cone. How is that possible if the velocities are different? Remember how we've said before, we've said A1 V1 is equal to A2 V2? So gravity's slowing it down. So the velocity up here, up top, the velocity is less. So how is it possible that Q in and Q out are the same? The area is getting bigger as it slows down. So it started off as like a really narrow diameter stream, and so as it goes upward, the jet area is increasing as the velocity decreases. So it's not like there's storage. There isn't storage. Q in equals Q out when we compare the flow rate here and the flow rate there. They're equal. It's just that the cross-sectional area of the jet is changing. All right, so that's a lot of information about problem 31. The key thing here is solving for V in the momentum equation. All right, so let's get some practice. Just refresh our memory of how to apply the momentum equation. We've got a black box that's changing these jets. There are 4 streams, 2 coming in, stream 2 and stream 4. Both of those fluid jets are coming in the X direction. And then there's a series of vanes and redirections, valves or whatever, that's sending the water out in the Y direction. And so what are the forces required to hold this black box steady in both the X direction and the Y direction? Like if I was going to put a pin to hold this in place, how much force should that pin be prepared to support to make it so that this black box doesn't shift sideways or it doesn't shift up and down, so that it's held steady? So what you'll need to do is apply the momentum equation in the X direction and then apply the momentum equation in the Y direction. And so we're going to try and solve for both sets of forces. And at this point, I hope you can be able to write the momentum equation just from memory, but in case not, some of the forces in the X direction required to hold the system steady is the sum of the flow through the control surface, mass flow rate out, velocity out in X, minus the sum of the flow through the control surfaces, mass flow rate in, times velocity in x. And then for y, it's the same thing except for we just change any place it said x to y. So we need to find the mass flow rates. And remember, account for the direction of the velocity. That's a key part of getting these problems right is the jet going to the left? Then it's negative. Is it going down? Then it's negative. In the x direction, we kind of already know just by inspection that there's going to be no force required to hold the system steady. The two streams cancel each other out. We kind of just already know that just by looking because, look, the two streams in the x direction are 2 and 4. 2 is to the left, and it's 0.3 cubic meters per second at a velocity of 30. Whereas stream 4 is half that flow rate, but double the velocity. So even when we convert it to mass flow rate instead of volumetric flow rate, it's going to be double the mass flow rate at 2, but half the velocity. And since it's in opposing directions, that means there's not going to be any force required to hold the system steady in x. Let's still run the numbers, though, and prove it to ourselves. And so that's what's showing on the screen right now is why the force required to hold the system steady in the x direction is equal to 0. So follow this same kind of analysis technique in y, and we'll find that actually there is some force required in the y direction. Before I show the y direction solution, let me just point out that when we were in the x direction, there's only in. There's no outflow in the x direction. And so that's why this first term in the momentum equation, sum of mass flow out, velocity out in x, there was nothing there. So all that we had when we actually solved for the sum of the forces in the x direction was the inflow streams. And so there was this minus mass flow rate 4, velocity 4, because of the minus sign in front of there. And then minus mass flow rate 2, velocity 2, because the minus sign distributes through to any of the terms that are inflows. But then keep in mind that velocity direction is important. And so here the negative sign of 30 meters per second for stream 2 is what ultimately caused this to be a net force required of 0, is because we had the minus sign that was built into it being an inflow for stream 4, but then we were minusing a negative due to the velocity at 2. Here's the solution in the y direction. So this is the opposite. Instead of having only inflow, in the y direction there's only outflow. And so here in the momentum equation, the second term having to do with inflow, we're just going to drop that off. It's just going to be the forces required are the sum of the mass outflows times the velocity out in y. Now the mass at 1 we can calculate based on the given flow rate, but then the mass flow rate at 3 we have to apply continuity, or the Reynolds transport theorem. It's going to be the mass flow rates in minus the mass flow rate out, and whatever's left over is coming out at 3. So there's 700 kilograms per second coming out at 3. Yeah?
If we would have had a force in the x direction, would we have had to do the square root, limit squared to get the total, or do you just want?
Good question. So how do you report your final answer, I think is what he's driving at. If you've got a force in x and a force in y, describe them just as their components. So in the exam or on the homework, just say the force of X and the force of Y. You don't necessarily need to combine them together. You don't have to say like the net magnitude and direction, just how much in X and how much in Y. All right, so the key to being successful in these is differentiating between in and out, making sure that you put the negative sign in if it's down when you're working in Y, or if the velocity is to the left when you're working in the horizontal plane. Are there any other questions on this problem? If not, let's get into the special case that is nozzles. Nozzles are interesting because when you draw the control surface, you are cutting through a pipe. And by nozzle, what we mean is a jet is coming out of one end, and the other end is connected to some sort of a pressure source. So it could be that there's a pump that's pressurizing a pipe, or it could be a pipe connected to a reservoir. So let's say that we have some reservoir, and then there's a pipe that's coming, and then it necks down to a nozzle, and then the water spraying out. So this is what we're talking about here. It's just that we're zoomed in on this section, and we draw a control surface on that section at the end. And so what we've got is we've got a jet coming out, but there's also water coming in to that control surface, and we have to account for it. But there's not just water coming in, it's pressurized water coming in. And so the water that is outside of the control surface, there is a pressure and an area that's pushing to the right. And so let me reproduce this sketch here on the whiteboard. We've got the water coming out, and then here's our control surface that we put here. There is a pressure inside the pipe that is acting as though it's an external force. So we've got some pressure in the pipe, and it's acting over a certain cross-sectional area, and pressure times area is force. And so the way that we now write the momentum equation for a problem like this would be pressure at 1 times the area at 1 plus some force required to hold the system steady is equal to the mass flow rate out, velocity out in x, minus the mass flow rate in, velocity in x. So what I'm saying is that the sum of the forces in the x direction required to hold the system steady, so that includes here the net effect of the pressure acting over some area, and then however much additional force you have to apply at the flange to hold the system steady. So these become a little bit tricky because it's both a momentum calculation and you have to do something to find out the pressure times the area. Here in this problem, we don't have the pressure given. So how do we find the pressure? If we know a jet of water and a change in velocity, can you think of an equation that tells you how the pressure changes in cases where you've got velocity changing as a function of position? In other words, we've got convective acceleration. What equation tells us pressure change from convective acceleration? It's Bernoulli's, right? So a change in velocity means there's going to be a change in pressure. So in a problem like this, we know here at 2, the pressure, because it's surrounded by air, the water pressure at 2 is 0. Now here at location 1, the water has some pressure, and you can calculate it by Bernoulli's equation. So in this example, I'd like you to try that. Find out what is the pressure at 1 based on the diameters that we're given. So the volumetric flow rate is 0.3 cubic meters per second. So let me write this on the whiteboard here. Q equals 0.30 cubic meters per second. And we know the diameter. d1 is 0.30 meters. So A1 is pi d squared divided by 4. And therefore, you can find out what is V1 based on Q divided by A1. All right, so you know V1. You can do the same kind of thing at 2, because you know it's the same flow rate. It's the same 0.3 cubic meters per second. It's just flowing through a smaller area. So the velocity is going to be higher at 2. So find V2. So we're going to say V2 is Q divided by A2. And now that you know the difference in velocities, P1 plus gamma z plus density v squared divided by 2, that's gamma z1, is equal to P2 plus gamma z2 plus density velocity 2 squared divided by 2. So this is Bernoulli's equation. And Bernoulli's equation is what we can find out what is the pressure inside the pipe. And we have to know the pressure inside the pipe to understand the true effect of momentum here in this nozzle. You'll notice on the screen here I simplified the momentum equation a little bit. Since the mass flow rate's the same in and out, I just kind of factored it. So see, mass flow rate out, mass flow rate in. Since the mass flow rate isn't changing, I just factored that out, so you only have to write it the single time. Okay, I got a couple of good questions as I was circulating around. One of them is, so this pressure 1, area 1, why is that on the left side of the equation instead of on the right side of the equation? And that's a really good point. So think about, here in the momentum equation, what we're saying is that if we're only having to deal with the mass flows, then this F sub x is the force required to hold the system steady. But now, on top of just the mass flow and velocity change, there's an external force that is on the outside of the control surface that we drew. And remember, when we cut this pipe, we didn't physically cut it. The reason why we're only seeing a certain pipe segment is because we drew a control surface. And so the water that's on the outside of that control surface, even though it's not actually a force, it's pressurized water acting over an area, the effect of that P times A is as though it's a force. And so we put external forces on the left side, and then what's left over, this F of x, is, after you account for the external forces, what force is required to hold the system steady. So let me just bring up my solution to make sure everybody got the same numbers. I think we were largely in agreement as I was walking around. Now you'll notice here in the sketch, I drew some force to the right. Now later on, when I do my numbers, my calculations, the number I got was negative. And so what that means is if I assume that positive forces in x are to the right, and in my calculations I get a negative number, that means that the force that should be applied is to the left. And I'll be sure to be explicit about that. Not only have I drawn the direction here, and then I get a negative down below, but then just off to the side, I also say in text, that means apply the force to the left. So always be sure about clarifying directions of forces. So we've got the jet with 0 pressure. We've got the pipe that's cut with some pressure that's non-zero. The mass flow rate, 300 kilograms per second. The cross-sectional areas allow me to get the velocities. Now, since we're squaring the velocities in the Bernoulli's equation, if you round off too soon, that can amplify error. So it's best if we keep like the full velocity to as many digits as we've got in our calculator. Keep all of that precision so that when you square it, it stays accurate. So I found the velocity at 1 is 4.24 meters per second. The velocity at 2 is 38.2 meters per second. And then Bernoulli's equation told me that the pressure inside of that pipe is 720,000 newtons per meter squared. You know, on the one hand, I kind of, as you were working, I was thinking, oh, should I put a question like this on the exam? And on the one hand, I thought, oh, but it's pretty hard, and they're just learning it on Thursday, and the exam's Tuesday. That's not much time for it to soak in. But, I mean, Bernoulli's equation, that's an old idea. That's not a new idea. So, I don't know. It's a toss-up. I'm still debating whether to give you one of these or a different type of momentum problem on the exam. We won't do like a vote, but I'm just letting you know what the internal monologue is, that, you know, this is something new, the fact that there's like an external force that's due to a pressure acting over an area, but really it's a concept you've seen before, identifying what is the pressure based on a change in velocity. Okay, so we did that and found the pressure at 1, so then we could substitute that into the left side of the equation, P1A1, and then we've got whatever additional force is required to hold the system steady. And then we've got the mass flow on the right side. So you can see to solve for f of x, I just moved the P1A1 over to the right side. This is something I always like to do to like find the result of these intermediate quantities, because it helps you to see like why the force is what you calculated. So 10,000 newtons approximately is due to the change in velocity. So of the force that you're applying to the left, 10,000 newtons of force you'd have to push to the right to account for the change in velocity. But that was greatly overwhelmed by the pressure inside the pipe. So when we actually have to push to the left, it's to resist the fact that you've got a pressure, a positive pressure going to zero pressure. That had a bigger effect here in how much you have to push to hold the system steady than the actual mass flow rate and velocity change. So then you'll notice here the text that I said was external force must be applied to the left to hold the system steady. So I've got the minus sign here, and I clarify that the force is to the left, even though up above I showed that the force was to the right. So this was saying the force is to the right, but the magnitude is negative, which means the opposite direction. So it's to the left. Okay, we all on the same page with this one? Okay, so you've got a homework problem where they want to know on a bend in a pipe, you're cutting it in two locations. There's going to be in the x direction a pressure and an area effect, and in the y direction you're also cutting the pipe and having a pressure and an area effect. But all they're asking for here is find the x component of the force required to hold the system steady. So here, let's think about the out and the in. Now, first of all, they tell you the pressure directly, so you're not going to have to use Bernoulli's equation to find the pressure. So we just assume that the water in here is 300 kilopascals, and they tell you the diameter of the pipe, so you can calculate the area. So P1A1 is going to be on the left-hand side of the equation. They give you the volumetric flow rate, so from that you can get the mass flow rate. And of course, this is a flow in, and in the x direction, there's no flow out. So if we go back to, how we were solving it here, you've got a mass flow rate, but there's no velocity out in the x direction on that homework problem. There's only a velocity in on that homework problem. So this may be even easier than the example you just solved. Has anybody heard of these before? LCACs? Landing Craft Air Cushion. It's essentially a gigantic hovercraft that's used for delivering amphibious vehicles and tanks during a littoral assault. Like the Marines, their focus is like amphibious invasions where they try and take a beachhead or go a certain number of miles onshore from a beach. And this is a way of getting a lot of men and equipment onto the beach very quickly. And they're big, 26.4 meters long, 14.3 meters wide. When they're fully loaded, they weigh 185,000 kilograms. So that's 185,000 tons. That's pretty heavy. You know, just for purposes of comparison, anybody know how many pounds a typical like semi-truck when it's fully loaded is? 80,000 pounds. So that's 40 tons. So a fully loaded semi is 40,000 40 tons. This is 185 tons. So it's more than 4 times as heavy as a semi. But in spite of that huge amount of mass, they can get up to about 80 miles an hour. They're really fast. And as you might expect, to get 80 miles an hour when you're carrying that much mass, it's just burning an incredible amount of fuel, 1,000 gallons an hour. Yeah, think about the cost of operating that. 1,000 gallons an hour. What is it now? Like about $2.50 a gallon? So you're paying a lot to run an LCAC, but I guess maybe if you're needing to land tanks on the beach, you're not worrying about the cost of fuel. Let's watch a video of one because they're kind of interesting. This is a perfect example of momentum and fluid mechanics because not only is it having to do with these thrusters, which is allowing it to steer, but the forward thrust is all about fluid momentum. And then you're also riding on a cushion of air. And so you think about, we said 185,000 kilograms of weight. So that all has to be resisted with pressure times area on the bottom. And so how is it, floating on a cushion of air? Well, they have to have an increased pressure on the underside of that LCAC. So let's do a quick set of calculations here. And let me give you this handout. First, do a little sketch of a hovercraft and show like the jet of air coming out and the air cushion. You let your inner artist shine today. Don't spend too much time on the drawing. What we really want to get at is these calculations. And so we're saying if we have the dimensions 26 meters long and 14.3 meters wide, so that's the area, and you know how much force it's going to support, the force associated with a mass of 185,000 kilograms. So remember, weight is mass times gravity. So how much air pressure has to be achieved to hold up such a great weight over a wide area? Okay, we just have about a minute left, so let me show you where this is all headed with the landing craft. So you already saw the sketch I put on the whiteboard there. There's an air cushion that holds it up, and then there's a jet of air that gives it its forward movement. So if we want to find out the air pressure that's required to hold it up, we need to convert the 185,000 mass into a weight. And so multiply that kilograms by G, and we get 1.8 million newtons. And then the cross-sectional area of that force being spread out on 26 meters by 14.3 meters. And so force divided by area tells you what the pressure is going to be. And so that is the air pressure underneath the hovercraft. And so 4807 newtons per meter squared is only about 0.7 psi. And so that's a really low pressure increase, but since it's distributed over such a wide area, that's why the LCAC is able to hold such a huge weight. Now, this part about trying to find out what thrust does it have, what force, the maximum force you're going to assume that the incoming air has a velocity of 0 and the outgoing air has this velocity of 150 meters per second. Actually, the faster it goes, the less thrust it's going to have, because the incoming air is going to have a velocity that's closer to the outgoing air. And so its maximum thrust is achieved when it's actually not yet moving. So this is, the weakness of one of our assumptions here is that this is the maximum thrust, but it would decrease as it is moving faster. And so we need to find, using the momentum equation, the mass flow rate out and the velocity out. So the velocity out was given as 150 meters per second. So then what we need to do is find the mass flow rate out. So it's going to be the volumetric flow rate, which has to do with the cross-sectional area and the velocity that's given, and then the mass of air, 1.2 kilograms per cubic meter. So if we have, for each of them, 275 approximately 1,000 newtons, then we can find the total mass of the total magnitude of the force. Then the last thing is just F equals ma to find out how much it could accelerate. Like its acceleration would be the overall force of the thrust divided by the mass of the body. And so it's able to accelerate about close to 3 meters per second squared. And that's pretty fast. If it was able to achieve that same thrust for a period of 60 seconds, then just by comparison, a Ford Mustang, which is going 0 to 60 in less than 5 seconds, it's accelerating at 0.56 g. And so this is like a little more than half that. So it can accelerate pretty fast. I wish they would have showed us that in the video, but that's just one other illustration of how momentum can be applied. I've kept you an extra 3 minutes, and so I owe you that 3 minutes back. I will repay it one day, a week from today probably. I won't kick you out early on exam day. Anyways. All right, so if you have questions as you get ready for the exam, please let me know. I'll see you on Tuesday for the test.